Good afternoon, geometry students. I hope that you're doing fantastic. We are going to do our notes for 9.3 today. These notes are super visual, so it can be helpful to have multicolors when you're taking them. I typically work with black, red, and blue, or black, pink, and blue. I have a red marker today that's coming out kind of pink. But, you know, if you have crayons, markers, pencils, any pens in different colors, that would probably make it a little bit easier. It's not essential, but if you do have colored markers, you might want to pause the video and go get those. So what we're going to look at in this lesson is basically the same right triangle over and over. It's going to be a right triangle that has a segment going from the right angle perpendicular to the opposite side. And what this segment is going to do is divide up the triangle into two smaller triangles. So I'm going to refer to this red triangle as the small one, and I'm going to refer to this blue triangle as the medium one, and I'm going to refer to the black one as the big one. Now, because these triangles end up being similar, and that is an important fact, we can compare the ratios of their sides. I'm going to label the side across from angle A with a little a. I'm going to label the side across from angle B with a little b, and the side across from C with a little c. Now, I can actually compare these triangles any way I want, big to small, big to medium, medium to small. I'm going to show you all three methods. So if we're comparing the big one, let's draw that in black, to the small one, and I want to look at two sides that I have information for on both. If I look at the red triangle, I can see that its hypotenuse is B, because that is the side across from the right angle. So I'm going to call this B. And if I want to know the short leg, I'll call that X here. I can just label it X. Because I've been told that these two triangles are similar, I can compare side to side. So C over B is going to be the same thing as B over X. The cool thing is, because I will have numbers for these when I do the specific problems in just a minute, I can actually solve for X. What I would have here is b squared equals cx, or when I take the square root, b is the square root of cx. So this just kind of gives you an idea of how we can compare. Method one would be big to small. We can also do, and I'm going to do this with specific examples in a minute, we can also do big to medium. And we can also do for method three, would be small to medium. So we can really compare any two of the three triangles. I wanted to show you this one using generalities, and then what I would like to do is show you the all three examples, all three methods using actual numbers, because I think it's going to be a lot easier to process when we have actual numbers to work with. So let's go ahead and compare the big to the small. And so if you want, you can keep the information that you had. But actually, no, I think this first example is going to be, yeah, I can do big to small. Okay, so you can keep, if you'd like, the triangles, but what we're going to do is just put specific numbers in so that it makes a little bit more sense. So let's assume that we have a large triangle here, and we're going to call this length 36, and then we'll call this our unknown right here. And if I want to, I can compare the big triangle to the smallest one. And even though I don't have much information, I can solve for the missing sides. So if we label the large triangle, we're going to label it as having a short leg of X and a hypotenuse of 36. Then when I look at the small triangle, it's going to have, if you look here, a hypotenuse of X And then I need this length here too. Let's put that in. A short leg of 5. Now what I can do is compare side to side. So I'm going to actually go from right to left because I think it might make a little more sense in this case. I can compare 5 to x, and it doesn't actually matter. You can go either way. And I can also compare x to 36. I'm just trying to make this example very similar to the one we just did. Now I can go, like I said, left to right or right to left, but I do have to be consistent. So I'm comparing short leg to short leg, hypotenuse to hypotenuse, and in this case I've chosen to go from right to left, but I could have gone the other direction, I'd get the same answer. All right, when I go ahead and cross multiply, I'm going to have x squared equals 5 times 36, or x squared equals 180. Then I take the square root, and I have to remember to do a factor tree anytime I think there might be pairs. So in this particular case, there are some pairs. So I'm going to have x equals the square root of, it looks like I have 2 2s, 2 3s, and a 5. So I can take out a pair of 2s, a pair of 3s, and my answer here is going to be 6 radical 5. So that would be how I could compare the big triangle to the small one to solve for x. Let's go ahead and try comparing the big one to the medium one. So I'm going to erase this work here. Again, if you need to rewind and pause the video so that you still have everything, please feel free to go ahead and do that. I'm going to do an example where it's going to be most helpful if I'm trying to solve for x to compare the big one to the small one. So let's say we've been given the information that this piece is 2, this is 7, and I'm trying to find x here. We might want to make a note that this whole side is 7 plus 2 or 9. Now in this particular case, since I'm trying to find x, I want to use 2 triangles that will end up having x. Notice that x is not on my small triangle, so I'm going to compare the big one and the medium one. So I'm going to draw my big triangle here, and I like to orient these the same way. I'm going to draw the medium one right next to it, pointing the same direction. Now on the big one, I'm going to label this hypotenuse as 9 and the long leg as x, just like I did on my picture. If I look at the blue triangle, I can see the hypotenuse, the one across from the right angle, is x, and the long leg is 7. And again, I can compare from left to right or right to left. 9 divided by x has to be the same thing as x divided by 7. When I cross multiply, I get x squared equals 63. If I do a factor tree for 63, 2 does not go into it, but 3 goes in 21 times, 3 goes in 7 times. I can see that x is going to be the square root of 3 times 7. I take out that pair of 3's and I get 3 radical 7 for my answer. So we can compare the big to the small. This case here, method 2 would have been big to medium. But because all 3 triangles are similar, if it's more helpful to me, I can also compare the medium to the small triangle. So let's do a third example where we're comparing different triangles. I'm going to erase the specific information from the last example, but the basic triangle shape is the same. And I'm going to change this to method 3. On method 3, I'm going to compare the small and the medium. Method 3, compare the medium and the small. It doesn't technically matter what order. For this one, let's go ahead and put an X here. Now notice that this X is on the small and medium triangles. So to solve for that, it's going to be most helpful to use the small and medium triangles. And then I have that this side here is 9 and that side is 25. So I'm going to draw my two triangles here. Let's do the small and the medium. So I've got the small triangle in red, and I have the medium triangle in blue. And again, I picked the small and the medium because I wanted a pair of triangles that had my unknown, had information that they could share. Now notice that this X is the short leg of the blue triangle, but it's the long leg of the red one. So we do have to be careful about that. And then the short leg of the red one is 9. And then the long leg of the blue one is 25. So again, because these triangles are similar, I can compare 9 to X and X to 25 and set up a proportion and cross multiply. Here, when I multiply, I'm going to have X squared. And here, when I multiply, I'm going to have 225. Now we get kind of lucky on this one. When we take the square root of both sides, I get 15. So we don't have to worry about pulling out pairs because it's just a perfect square. Now let's go ahead and do a word problem using this type of triangle. So I'm going to read you the word problem. And then we're going to use the triangle we just talked about to solve it. So in this particular example, we've got some bleachers at school. I think we're getting ready for a football game or something here. So let's see. Grant wants to hang a banner from the top of the Westland High School grandstand to announce the beginning of spring track practices. How long can he make the banner? So we've got the grandstand here, and we can see that we can draw a right triangle off to the side here that has a length of 10.5 here, X here, and then on this little piece right here, it's 5.75. So this is going to be most similar to the last example we did, because we can see, based on the information that we're working with, that it's going to be most helpful to deal with the two triangles on the inside of the larger one because of the information that I've been given. So I'm going to draw the medium triangle and the blue triangle, the medium triangle and the small triangle down below here. That's my medium triangle. Here's my small triangle. And I'm going to label them with the information I have. Now, notice that the X in this case is the long leg of the blue triangle. And then for the red triangle, I have the short leg at 5.75 and the long leg at 10.5. And the 10.5 is also the small leg of my blue triangle. I need to be able to label the same two sides on both triangles. In this case, the short leg and the long leg on each. All right, now I'm going to compare and say that I know 5.75 over 10.5 has to equal 10.5 over X. Now, in this particular case, we don't end up with an X squared, but that's okay. We can still cross multiply. So we're going to get 5.75X equals 10.5 times 10.5. Or 5.75X equals 110.25. Then I just need to divide both sides by 5.75. And I get that X is 19.2. So that would be this length right here. Now notice that the banner could run the whole length of the grandstand. So the length of the banner could be 19.2 plus 5.75. We want to line up our decimals there. And then we would have a 5 here, a 9 there. That if we round here, we would get 24.95, or we could round to approximately 25 feet. So the banner could be approximately 25 feet. Now, I don't know if you know this, you probably have not been taught this before, but what we've been working with this entire lesson is something called geometric means. Geometric mean is another kind of average, and you basically get it when you're setting up a proportion and the bottom left number and the top right number are the same. Then these are called your means, and the other two numbers are called your extremes. So we're going to do a little mini lesson on geometric means. It is part of lesson 9.3, and it's what we've been doing all along here. But we're going to learn how to look at the means and extremes without the triangles. So, for example, let's write here, if we want to find the geometric mean of, let's say, two numbers A and B, we set up the proportion A over X equals X over B, and we solve that proportion. We get X squared equals AB, take the square root, and the geometric mean, let's call the geometric mean X, would just be the square root of A over B. Now, this is what we've been working with on all of the last problems that we did, but like I said, now we're going to do it without the triangles. So let's say we want to find the geometric mean of 3 and 27. We would set up this proportion right here with 3 on the top left, 27 on the bottom right, and X's in those spots there. So we would write 3 over X equals X over 27. We would cross multiply. We get X squared equals 81. And when we take the square root, we get that X is 9. Okay, let's do another geometric mean problem. Let's do the geometric mean of 2 and 6. Again, we would take 2 over X and set that equal to X over 6. We cross multiply and get X squared equals 12. And remember, anytime we're taking the square root, we need to pull out pairs. 12 is 4 times 3, which is the same thing as 2 times 2, 12 is 4 times 3, which is the same thing as 2 times 2 times 3. So if we take out a pair of 2's there, we get 2 radical 3 for our answer on that one. So finding the geometric means without the triangles is relatively straightforward. In the notes that I had handed out, and again, we're not doing handout notes during distance learning just because of the difficulties of printing, plus we're doing shortened abbreviated notes so they wouldn't match anyway to what we had before. But typically I do like to do a little bit of review of radicals. So just we'll just do like maybe 3 radical review problems. One thing I want you guys to keep in mind is if you're taking the square root of a fraction, the quotient property tells us that we can divide that up. So this, for example, would become 2 over 3. The product property, so this would be an example of the quotient property. The product property tells us that we can multiply 2 radicals. So for example, if I have the square root of 3 times the square root of 6, that's the same thing as the square root of 18. Which would be the same thing as 3 radical 2. And then the last thing that we did a little bit, I think in our notes yesterday, is rationalizing the denominator. So just to review this, to rationalize the denominator, let's say that our answer was the square root of 1/2. We could write this as the square root of 1 over the square root of 2, or 1 over the square root of 2, but we can't leave a radical in the denominator, so we would have to multiply top and bottom by radical 2. And that's what we would get there. So just a little mini review of a few things to do with radicals. I know these notes were super long. I'm proud of you for hanging in there, and have a good night, guys. Bye.